So if we want to model CVR effect in Milsoft, then what we need to do is we need to go in and change the coefficients on our load model. So in Milsoft, we have the opportunity of using a mix of constant impedance, constant current, and constant power load. From a presentation that was given at a users conference, they actually gave some suggested ratios for how this would be set up. So if we were going to look at like a residential summer peaking sort of a load where we're going to have air conditioning, we could add like a 30% impedance to this to kind of better represent the effect of the air conditioning and how it's sensitive to voltage. If we had summer peaking load with minimal air conditioning, we would go with a 30-70 type of a mix. And then if we were talking about like residential winter peaking, you would use like a 30-70 mix, industrial 80-20 mix as far as power versus impedance, and commercial 50-50. So anyway, these are just some guidelines that are provided by Milsoft in terms of how you might want to adjust these values. And to do better than this, you probably have to do some measurements on the circuits you're working with to see exactly what those factors would be. So these are just kind of some default assumptions based on their experience. So if we were going to go back and change like a circuit, and let's go ahead and look at the circuit that was used last year for project part 3. This was basically the substation. We had a regulator here kind of toward the top of the feeder. We had some capacitor banks in here. And what we could do is we can control these devices to get a CVR effect. More specifically, we'd want to drop the voltage. But before we do this, what we'd have to do is we have to change the nature of the load model. So right now, if you look at the default load mix model, it's set up to be 100% on constant power load. So what you would do is you'd go in and change this and look at like a 30% constant kVA, 70% constant impedance mix. What you would see when you rerun the power flow is that the load stays the same. This load component stays the same, but what they have in here is what's referred to as an adjustment factor. And what it's doing is it's adjusting the load model to take into account the fact that you've got now you have a constant impedance characteristic associated with it. So this is what WindMil would do, is it would make an adjustment in the load because of this. And what you're going to have for the top of the circuit now is, instead of having 16,971 kilowatts, you'd have 16,545 kilowatts. Now, if I had some load allocation measurements, what I could do is I can run this again, but I just didn't want to rerun the load allocation again. So here's our new baseline right here. Our baseline, if I have the constant impedance load component, is that we have the top of feeder kilowatts, 16,545. If I want to model now a CVR type of a scheme, then what I would do in this case, I would go ahead and I would drop the voltage at my regulator. So instead of having 124, let's say, I could drop this down to 121. Right, and so what you see is at all these different points where I'm regulating voltage, I'm going to have this lower voltage set point in this case. And what you see now is that we're going from 16,545 to 15,983 kilowatts. All right, so the reduction in this case is 562 kilowatts. And so what this kind of shows is, what would be the impact of deploying a scheme. You could actually kind of estimate this in a program like WindMil. Now, you can also do this modeling in OpenDSS, and this lecture is running a little bit long, so I'm not going to get into too much detail here because you're already kind of looking at this in your project. But what we can do, if we wanted to do look at integrated volt var control, is we can go ahead and look at the impact of the regulator and the capacitor operation. And you do have like a local control model you could use in OpenDSS. It has similar sort of settings that what you would see in WindMil, except one thing that's different is you could set up a delay. In this case, this is a delay in operation for when you go outside the bandwidth, how long you're going to wait till you do the switching or not. And then what you'd have for the capacitor is you'd have the capacitor itself, which you can have on or off. You can have like what's the initial state of the capacitor if you're implementing a control. And then you would then model your capacitor control separately. And what you can do is you can set this up based on current or voltage or kVAR, power factor, time, whatever. And then you could set it up in terms of a threshold and when to turn on and off the capacitor bank. You can also make the measurement of this be at another location. It doesn't have to be right where the capacitor is at. So then if you wanted to do like capacitor control, you could define like these two 1200 kVAR capacitors. And if you wanted to set up control on cap 2, you can have the initial state as 0. And then what you can do is you can have the on setting set up where it's, say, based on time, let's say. And so what we're doing in this case is we're turning it on at 4.5 hours and we're turning it off at 11 hours. This would be kind of like a time-based control. And you could set this up for switching on kVAR to certain line segment, say at the substation as well. So what you'll see in this case, you know, say we have the time-based switching, then you could see all of a sudden at the substation, the VAR flow would be changing. As soon as the capacitor switched on, the kVAR coming from the transmission would drop down. When we switched the capacitor off, the kVAR would jump back up. And then when we had the regulator operations, I'm showing the voltage in this case, but you can kind of clearly see the impact of the tap changes where the tap's jumping up, jumps up again, gets up to this point, and the tap drops back down again. And you see when you're modeling the line regulator, you could see these variations and you can see these rapid fluctuations in voltage. If you wanted to model a centralized algorithm in OpenDSS, what you would need to do is you would need to write a driver program where this is running from MATLAB or for Python. This is a little bit of beyond the scope of this class this semester. But what you could do is like for that heuristic control that I talked about earlier, you can actually implement that in MATLAB or Python. And then you could send commands to the OpenDSS engine in terms of whether you want to have the capacitor on or the capacitor off as a function of your measurement set. So as far as a few references, this was the Baran-Borzone paper I was referring to earlier. As far as use cases for volt VAR control, there's an EPRI directory that talks about the different sort of strategies you might want to implement. And then there's some interesting things up on this IEEE website. This is a volt VAR task force where they have, you know, a group that's set up for looking at this. As far as what these CVR coefficients will look like and doing a business case analysis, this is a pretty good reference. This was a study done in the Northwest United States, actually, as far as looking at the benefits of CVR. And then this is a paper I've used before, but as far as a lot of the CVR stuff we've been looking at in our class projects, a lot of it's outlined in this particular presentation here. All right, so this is all I've got right now for the volt VAR strategy. And again, as I mentioned before, you know, a lot of utilities are using this. However, how you come up with this control takes a little bit more analytical horsepower than we've actually covered in this class so far. You really have to kind of get an optimization theory, but at least you kind of know, you know, what we're trying to do when we implement this sort of a control. So that's all I've got right now for this, and what we'll be looking at in the next few lectures are some other smart grid applications as well.